I'm gonna talk about polynomial time guarantees for the Burer-Monteiro method. And this is joint work with Ankur Moitra from MIT. So this talk is going to be mainly about semi-definite programming. So let me start simply by introducing the notion of a semi-definite program. A semi-definite program, which I'm gonna abbreviate as SDP, it's a special class of optimization problems that has the form that you may see on this slide. And perhaps the most important as for now is that the optimization variable, which I'm denoting as capital X, is actually a matrix. So the variable capital X is a matrix. Furthermore, it's actually a symmetric matrix of size n times n. So yeah, so that's the formally how we write an SDP, but the exact formulation is perhaps not totally important for us for the purpose of this talk. What matters for us is that semi-definite programs are actually very well behaved. They are very well behaved class of optimization problems. In particular, they are convex optimization problems. Furthermore, they can be solved in polynomial time using techniques such as interior point methods. And this is something that we have known for a while. We have known for a while that interior point methods solve SDPs in polynomial time due to the work of Nesterov and Nemirovsky. And importantly, also SDPs actually appear in many different applications in science and engineering, and I will illustrate a few of them in the next slide. The main purpose of this talk is going to illustrate that we can also solve SDPs in polynomial time using a more recent class of methods. And this more recent class of methods is what we will call the Burer-Monteiro method. And I will introduce this later in the talk. So first of all, so here are some applications of SDPs in case that you haven't heard about them before. For instance, semi-definite programs appear in the context of the max code problem. So this is a classical problem from computer science and combinatorial optimization. And it turns out that the best polynomial time approximation algorithm that we know is based on SDPs. They also appear, for instance, in the problem of matrix completion. There are very good SDP relaxations that approximate this problem. Similarly, they have also been used in the context of phase retrieval, in rotation synchronization, which is a problem that appears often in robotics and also in cryo-electron microscopy. And they appear as well in problems from machine learning, such as clustering problems. So these are some of the applications of SDPs, and there are many other practical applications of semi-definite programming. So solving semi-definite programs, as I mentioned before, like one approach to do it is by using interior point methods, and we know, like as I mentioned before, we know that interior point methods can solve SDPs in polynomial time. And yeah, for instance, Frank talked about this on Tuesday, I believe. And interior point methods, they are widely available. So there are many different solvers many different implementations based on interior point methods. But one inconvenience of interior point methods is that for large scale SDPs, they are typically intractable. They typically do not perform very well for large scale problems. And in particular, the reason is that very often they run out of memory. And as a consequence, in the past years, let's say in the past decade, there has been a surge of new techniques for solving semi-definite programs that scale better for large scale problems. And in this slide, you may see a few of the alternatives that have been proposed for solving large scale SDPs. The main topic of this talk is the first of these methods. Namely the low rank factorization method, which was pioneered by Burer and Monteiro. And I'm going to refer to this method as the Burer-Monteiro method. And importantly, this Burer-Monteiro method is one of the most widely used methods in practice for solving large-scale semi-definite programs. So let me try to illustrate what are the main ideas behind this technique. So here on the top, I have a semi-definite program. This is the formulation that I had at the beginning. And as I mentioned before, the exact form is perhaps not terribly important for us now. What matters the most, again, is that the optimization variable X is a symmetric matrix of size n times n. Furthermore, this matrix X is actually positive semi-definite. And consequently, it's possible for us to factorize this matrix X in the form Y times Y transpose for some other matrix Y. And we're gonna make the assumption here that the matrix Y, it's actually going to be a tall and skinny matrix. We're gonna assume that this matrix Y is gonna be of size n times P, where P, which is the number of columns, is significantly smaller than n, which is the number of rows. So that's one of our assumptions. So we are going to assume that there is a solution of the SDP that has a small rank. And it turns out that this will always be the case, and I will discuss this later. We are going to assume that there will be a solution of rank P where P is much smaller than n, and we're going to use this in order to factorize X in the form YY transpose, where Y is a tall and skinny matrix. And now we simply rephrase the problem in terms of Y. So here I have the new problem written in terms of Y. And the Burer-Monteiro method, the main idea is simply to solve this new problem. We now are going to solve this new problem by using some local optimization method. Now, why is it the case that this might be a good idea? Well, the main advantage of solving this new problem is that the matrix Y that we're using, it's smaller than X. Since we are assuming that P is significantly smaller than n, then the matrix Y, which has dimensions n times P, is going to have significantly less entries than X, which was the original variable. And consequently, when we are going to try to solve this new problem, we're going to get an immediate gain in terms of memory usage. So there will be a direct gain in terms of memory usage. And as I mentioned before, memory was actually the bottleneck for interior point methods. And what that means is that this memory improvement, it's actually very significant. Okay, so now what's the next question? So another question one question that I forgot to mention before is how is it that we are supposed to choose P? So the assumption was that the optimal solution of the SDP had a small rank, let's say rank P. But how is it that we are supposed to know this rank P in practice? Well, in some cases, we know something about the problem. There are some problems in which we know something about the problem, and we may have an estimate about this value P. But it turns out that in the worst case, we can always use this bound that I have here in the bottom. And what this says is that if we choose P to be about a square root of 2 times M, where M is the number of constraints, that's always going to be enough. So there is a bound, there is a value of P that we can always use, and if we choose this value of P, it turns out that the problem that I have on the top and the problem that I have in the bottom are going to be equivalent in the sense that they have the same optimal value. So as long as we choose this value of P that satisfies this bound, which I'm going to call the Barvinok-Pataki bound, the two problems are going to be equivalent. Nonetheless, there is an important distinction between the problem on the top, which is the SDP, and the problem in the bottom, which is the Burer-Monteiro problem. And the important distinction is that the original problem, the semi-definite program, is a convex problem. It's a very well-behaved problem. But the problem in the bottom, it's actually a non-convex problem. And what that means is that if we use local optimization method to solve this problem in the bottom, in general, we might get stuck in a local minimum, which might not be global. And if that's the case, we will not be solving the semi-definite program to global optimality. So that's one important issue. Well, the Burer-Monteiro method was introduced around 20 years ago. And since then, there has been quite a lot of research in trying to understand the behavior of this technique. And because of that, we now understand that there are two important regimes to take into account. The first regime is when we choose the parameter P. So P is the number of columns of the matrix Y. This is a very important parameter of this method. And if we choose this parameter below the Barvinok-Pataki bound, it turns out that the behavior is actually quite bad. In the sense that even if we assume that the Burer-Monteiro problem is equivalent to the original problem, in general, there might be a spurious local minima, which means, again, that if we use local optimization, we might not get the solution that we want. But as long as we choose the parameter P above the Barvinok-Pataki bound, it turns out that the situation dramatically improves. So let's assume for the remaining part of the talk that we choose P above the Barvinok-Pataki bound, which is a square root of 2 times m. In this regime, early work by Burer-Monteiro and also by Journet and co-authors gave us strong indications that this method was likely going to be actually quite successful. But a formal proof was came later, and it was given by Bumal, Voroninski, and Bandera. And what they showed is that under certain conditions, in particular, if we assume that the cost matrix is generic, they were able to show that the Burer-Monteiro problem is going to have no spurious local minima. And hence, if we find any local minima, that's going to be enough. Sorry, give me a minute. I apologize. Okay, so let me continue. So yeah, so this work by Bumal, Voroninski, and Bandera says that under some conditions there's going to be no spurious local minima. And there was some subsequent work, in particular by Bumal and co-authors, which proved that some extensions of this result, which deal in particular to the case where we may have some approximate local minima. So
Diego, sorry,
yes.
Diego, let me ask you a question. This is something I never understood. So in here, this assumption that the feasible set is smooth. This is a feasible set of the semi-definite problem.
Of the Burer-Monteiro problem. The feasible set of the Burer-Monteiro problem. So the reparametrized set.
Yes, but you have the constraints, right? This
yes.
is with the constraints.
Yes.
So isn't it true that there's cases where this set is never smooth? Like for certain combinations of the dimension and the...
No, that's not the case. If we, for any dimensions that you want, if you take generic matrices, it's the feasible set will be generically smooth.
Okay. Okay. Thank you.
Yes, and actually the smoothness of the reparametrized feasible set actually is going to agree with the primal non-degeneracy of the original SDP. So there's an interpretation of this smoothness also in terms of the original SDP. Okay, so let me perhaps move on. So above the Barvinok-Pataki bound, the situation is a lot better behaved. But I still would like to point out that even though we know about these results, prior to our work, actually, it was still unknown whether it was possible to solve SDPs in polynomial time using the Burer-Monteiro method. We have known for a very long time that we can solve SDPs in polynomial time using, let's say, interior point methods. But until quite recently, it was still unknown whether we could achieve similar guarantees using this widely used Burer-Monteiro method. And it turns out that one of the main obstacles was actually feasibility, because all the previous works assumed that we were able to obtain a solution that satisfied the constraints exactly. And doing that in practice, it's not going to be feasible. So our main result is stated on this slide, is this theorem on the bottom, and it has 3 main assumptions. Let me perhaps just focus on the first assumption, which is the most important one. And what this assumption says is that I want to choose the parameter P slightly above the Barvinok-Pataki bound. So notice that I want P to be above a square root of 2 plus eta times m, where eta is a positive constant that is fixed, but it can be arbitrarily small. For instance, it can be 0.01. So that's the main assumption, and under this assumption, what we can show is this theorem on the bottom. And what does this theorem say? So the theorem says the following. if you give me an arbitrary semi-definite program that satisfies some smoothness conditions, and you then perturb the cost matrix by using a small random perturbation. So this is important. We're going to take a small random perturbation of the cost matrix, and we are now going to try to solve this perturb problem. And we are going to solve this perturb problem by using the Burer-Monteiro method, and in the sense that we are going to initialize some local optimization method with an approximately feasible point. And what this theorem shows is that the Burer-Monteiro method is able to compute a point that is approximately feasible and approximately optimal with high probability in polynomial time. And this high probability result, this is with respect to the random perturbation that we took at the beginning. So here we have to take a small random perturbation, and with high probability with respect to this perturbation, the method will conclude in polynomial time. Any questions here? Okay, so let me perhaps discuss a little bit more this issue of the random perturbation. So this idea is actually, it's not new. It's something that is known as a smoothed analysis, and this is an idea that was introduced by Spielman and Tenk in 2001. And the motivation behind smoothed analysis is that there are some algorithms that are very practical, but that might be slow in a few very specific instances. And one notable example is the Simplex method. The Simplex method for solving linear programs is a very efficient method in practice, but there are some very specific instances for which the method can take exponential time. And what Spielman and Tenk said is that in order to analyze these methods, it's better to take a worst case instance, but then to take a random perturbation around this worst case instance. And that's the notion of a smoothed complexity. That in a smoothed complexity, we start with a worst case instance, then we take a small random perturbation, and we analyze the complexity of this random perturbation. And in particular, they use this technique in order to show that the Simplex method takes polynomial time in this setting of a smoothed analysis. And the theorem that I showed you in the previous slide, what this theorem is doing is exactly the same. We start with a worst case semi-definite program, and then we slightly perturb the cost matrix using a random perturbation. And we show the polynomial time optimality of the Burer-Monteiro method. And what this says is that the Burer-Monteiro method takes polynomial time in the setting of a smoothed analysis. Let me also point out another important issue here, which is that this theorem alone is actually not enough for us to guarantee that we can solve SDPs in polynomial time. And the reason is that there's actually one assumption here that it's actually that it's a little bit tricky, which is that we are assuming here that we are initializing the Burer-Monteiro method with a point that is approximately feasible. And what that means is that we need to find this approximately feasible point. And this is something that is non-trivial. Simply finding an approximate feasible solution of a semi-definite program can be quite complicated. So let me make this more precise. So we want to find a matrix X that satisfies some constraints approximately. So we want something that is approximately feasible. And also I want the matrix X to be positive semi-definite. How is it that we can do that? One possibility is to formulate this problem as a least square problem, where we minimize the sum of the squares of the infeasibilities. And once we have this new formulation, we can apply again the Burer-Monteiro method by factorizing X in the form Y times Y transpose. And if we do that, we obtain a new optimization problem in terms of Y. In this case, this is an unconstrained optimization problem in terms of Y. But as before, this is a non-convex optimization problem. But despite the fact that this new problem is again non-convex, we can show that under the same assumptions as before, if we randomly perturb the data of the SDP, then we can find a point which is approximately feasible for the SDP in polynomial time using the Burer-Monteiro method. And that's the second theorem that I have here in the bottom. So, and now if I combine these two theorems, polynomial time optimality and polynomial time feasibility, we have a two-stage method for solving worst case semi-definite programs using the Burer-Monteiro method, and everything runs in polynomial time. So first we find an approximately feasible solution using the second theorem, and then using this initial point, we can find an approximately optimal solution using the theorem on the top. Any questions here?
Can I ask a question? I don't know if you can hear me, Diego.
Yes, I can hear you.
So in the first theorem, what is so approximately feasible and approximately optimal? So what is the approx? I mean, and so is this and how does this affect the number of iterations? I mean.
Yeah, so the accuracy is going to be proportional to the perturbation. It's going to be proportional to sigma, to how much you're gonna perturb. So so essentially, you can fix an arbitrary perturbation, you can fix an arbitrary precision, and then you can choose sigma to be proportional to that.
Oh, I see. Okay. Okay. Good.
Any other questions? Okay. So what I want to do now is to try to give you some of the ideas behind the proofs of these theorems. And yes, and actually the main ideas behind of our theorems actually rely on the results of Bumal, Voroninsky, and Bandera. What they showed is that they provide a very explicit characterization of when is it that a semi-definite program may have spurious critical points when we solve it using the Burer-Monteiro method. So this theorem here says that the Burer-Monteiro problem is going to have spurious critical points only when a certain condition is satisfied. And the condition is that the cost matrix of the SDP has to lie on a certain set. And this set is what I'm calling here M plus L. So this is a certain variety, and it's an explicit one. So M consists of all matrices of up to a certain rank, and L is the linear span of the matrices that define the SDP. So there's an explicit condition that characterizes when is it that spurious critical points may exist. And now, importantly, so this theorem also tells us why is it that the Burer-Monteiro method, why is it that the Barvinok-Pataki bound is relevant? Because it turns out that when P is above the Barvinok-Pataki bound, then this set M plus L is going to be a low dimensional set. It will be a variety of low dimension. And if we have a low dimensional algebraic set, and if I pick now a random point, let's say a random cost matrix, then with probability 1, this random cost matrix is not going to lie on such a set because it's a low dimensional set. And that's the way in which Bumal, Voroninsky, and Bandera were able to show that for a generic cost matrix, the Burer-Monteiro method doesn't have any spurious critical point. But as I mentioned before, this is not enough to guarantee polynomial time optimality, because for polynomial time optimality, we have to acknowledge that a numerical solver will never be able to obtain a point that satisfies the criticality conditions exactly. There will always be some mistake that the solver is going to make. So in order to address that, what we do is that we provide a characterization of a spurious approximate critical points. And the characterization is actually quite similar to the characterization from before. What we showed is that spurious approximate critical points may only exist when the cost matrix lies on a tubular neighborhood around the set M plus L from the previous slide. And what do I mean here by a tubular neighborhood? Well, I mean precisely what you may see on the picture on the right-hand side. So we have a set, for instance, a curve, and then we simply thicken such a set by an epsilon amount. That's the epsilon neighborhood. And what this theorem tells us is that if we want to understand how often the Burer-Monteiro method is going to be successful, then we need to understand the volume of such a tube. And now, importantly, it turns out that volumes of tubular neighborhoods actually have quite a rich history in differential geometry and also in algebraic geometry. In particular, here I have two theorems. The theorem on the top gives us an explicit formula for the volume of a tubular neighborhood around a manifold. So this is a theorem from a book of 1939. So this is a relatively old result. And it gives us an explicit formula for the volume of a tubular neighborhood around a manifold in terms of the curvature constants of the manifold. Now, in practice, computing these curvature constants can be complicated. So applying this theorem is not so easy to do. But in the case of algebraic varieties, there is a more explicit formula that it's easier to apply. And that's this theorem that I have here in the bottom. This is much more recent, as you may see here. And what this theorem says is that if I have a variety, there's again going to be some explicit bound on, well, in this case, it's on the probability that a random point lies on such a tubular neighborhood. And the bound now depends on some very explicit constants, which are in particular the ambient dimension, the dimension of the variety, and for instance, the degree of the defining equations. And this second theorem is actually the key for us in order to prove the polynomial time guarantees. So let me perhaps just give you the main sketch of the proof. So this is our main result, where we showed a polynomial time optimality of the Burer-Monteiro method. And the main idea for this proof is the following. So first, we showed that the Burer-Monteiro method is able to find an approximate critical point in polynomial time. That's the first step. This is actually not so trivial, but let me skip this part. Now, assuming that we have an approximate critical point, our hope is that such a point will be the global optimum. So what we will try to do is to understand what is the probability that this critical point is not the global optimum, or equivalently the probability that this point is spurious. Now, since we have a characterization of spurious critical points in terms of tubular neighborhoods, we can upper bound this probability in terms of some tube condition. And finally, using the explicit bound from the previous slide on the volume of a tube, we can find an upper bound on such a probability. And if we just evaluate the constants, we will figure out that this probability is actually a tiny number, which means that the probability that the point is spurious is going to be a tiny number. And hence the Burer-Monteiro method will find the global optimum with very high probability. That's the main idea behind the proof. So let me perhaps remind you that there was a second theorem regarding feasibility. And it turns out that for feasibility, a very similar analysis holds. So there's also going to be a tube characterization of when is it that there might be spurious critical points for the feasibility problem, for the least square problems that I have here on the top. And then we can use this tube characterization in order to provide, to prove that we can find an approximately feasible point in polynomial time. So we also provided some experiments, some computational experiments in order to complement our theoretical results. So let me perhaps briefly talk about this. In this first slide, we illustrate, we are trying to illustrate what is the role of this Barvinok-Pataki bound. And for that, we generated a set of random semidefinite programs. So we generated some random semidefinite programs, and we solved these random SDPs using the Burer-Monteiro method for different values of the parameter P. And what you may see on this plot is the percentage of experiments which are solved to global optimality when we use the Burer-Monteiro method. And what you may notice here is that there's actually a very steep jump when we cross this vertical line. And this vertical line, as you may expect, actually corresponds to the Barvinok-Pataki bound. And this shows that the Barvinok-Pataki bound is something that it's not an artifact of the analysis, it's something that actually you can also see in practice. Now let me illustrate a second experiment. And in this experiment, we are trying to illustrate what is the role of the random perturbation that we are taking. And for that, what we did was that we considered a semidefinite program that was actually quite ill-behaved. We considered a quite problematic SDP for which the Burer-Monteiro method was only successful 50% of the time when we tried different random initializations. And then what we tried to do was to add different levels of noise around such an SDP. And what you may see on this plot is that by adding increasing values of noise, we are able to overcome this the inconvenience that we have with this original problem. And what this means is that the role of the noise is simply that it allows us to move away from problematic instances. And the picture that we have here on the right-hand side, it simply compares how are the residuals behaving when with the number of iterations for the original unperturbed problem and for the perturbed SDP. And what you may notice in this plot is that the residual decay much faster for the perturbed problem. So that's really all I wanted to say today. So just to summarize, we proved the first polynomial time guarantees for the Burer-Monteiro method. Importantly, these guarantees work arbitrarily close to the Barvinok-Pataki bound. And our proof actually relies on very geometric ideas, such as the notion of varieties and tubular neighborhoods around varieties. And that's it. Thanks for your attention.
Great. Thank you, Diego, for your presentation. Any questions or comments?
I have a quick question on picking the rank here. So practically, in some instances, you'd want to pick the smallest rank that you could. But is there any advantage to picking even larger than this minimal Barvinok-Pataki bound, in the sense of you might converge faster, there are fewer bad instances? Like, is there any advantage to picking a higher rank?
Yeah, in practice, typically you want to choose the smallest rank that you can, and actually the Barvinok-Pataki bound is quite high compared to what people actually use in practice. In practice, people don't even go to that level. In terms of the analysis, it turns out that the probability that the method will be successful is actually going to depend on that rank. So yeah, so this inequality that we have here, there's like some approximation here in the sense that somehow the higher we are from the bound, so the higher that we are from a square root of 2 times m, the higher the probability that we will be successful. But in any case, for any value that is larger than a square root of 2 times m, it will be high probability, just that it will be slightly larger if you choose the rank higher. So that could be that's perhaps one advantage. Does this answer your question?
Yes, thank you.
Can I ask a question?
Sure.
Yeah, so it's about, I mean, again, the accuracy that I mentioned. So, I mean, so in the interpoint method, when we say it's polynomial time, usually, I mean, the polynomial time, it's polynomial in log of 1 over epsilon. So epsilon is the accuracy. And the fact that it's log of 1 over epsilon, not 1 over epsilon, I think is kind of important here. So is there actually a hope, since sigma you said is the accuracy, is it possible to actually improve this sigma inverse to like a log 1 over sigma? Or is there, I mean, is this possible, or this, I mean, there is kind of
I think that it's possible that it will be, I think that it's possible, but our current analysis, the ideas that we're using right now are really not going to lead to such a bound. Ideally, we would really like to have a polynomial dependence on log of epsilon, as you mentioned. But our techniques, in particular, the use of these two bounds, which is one of the key parts of the paper, these two bounds are going to have a dependence which is polynomial in epsilon. Okay. So whenever we use these two bounds, we will not have this logarithmic dependence. Okay.
And so maybe another question is, so you have this phase 1 where you find an approximately feasible point. So here there are no actually constraints. So and so you apply a factorization again. So I don't know. Yes, in this one. No, the previous slide, maybe. Yes, this one. So okay, so yeah, so you see in the last displayed equation, your y is actually of the same size as x, right?
My y, no, it's not of the same size as x. I'm doing exactly the same factorization as before. Y is of size n times p.
Oh, okay, because you wrote y is in Sn. I mean, I thought it was.
Okay, yes. So this is a typo. Thank you. So okay. This y should be of size n times p.
Okay.
And yes,
I mean, because you don't have, I mean, in SDP, LS, the least square, you don't have actually any constraints. Right. So there are, I mean, this Barvinok-Pataki kind of argument is not, yeah.
You're completely right. So actually, prior to our work, I don't think that it was known whether there was an optimal solution to this problem that had a small rank.
Okay.
But actually, it is. So there will always be an optimal solution of this problem that has rank at most a square root of 2 times m, where m is the number of squares that you have in this summation.
Okay. Good. Okay. Thanks a lot. Yeah.
No problem.
Is there anywhere where you needed an assumption that the original SDP had strict feasibility?
Strict feasibility, no, I don't think that we are making the assumption. I'm trying to think, but I don't think that we are making the assumption. We do need that there's a strict duality.
But then how do you know when you perturb it that it remains feasible? I mean that there's a solution.
You're right. You're right. I think that these results, well, in particular, these results assumes that you start with a point which is approximately feasible. So there's some assumption here already that we are assuming that there's an initial point that is approximately feasible. We are assuming that the perturb problem has a point that is approximately feasible for this theorem here. But yeah, no, I don't think that we're making any assumption about the strict feasibility of the problem.
So that should be an approximately feasible point of the perturb problem.
Exactly. It might be infeasible, but as long as there's a point that it's approximately feasible, then that's enough.
But you're perturbing C. That's the objective, right?
Yes. Oh, yes, yes. So here we are perturbing C. You're right. So we have these two theorems. We have these two theorems in the first, in the optimality, we only perturb C, so that doesn't change feasibility. So in principle, this problem could be infeasible as long as there's an approximately feasible point. That's enough. Sorry, Pablo,
because in that case, you shouldn't expect to get the kind of polynomiality that Hamza was talking about, right? Because we don't know actually if when you have a semi-definite program which is not strictly feasible, if you can solve it in polynomial time.
I see.
Right.
I think that I will probably have to look more carefully about the assumptions that we're making, because of course these assumptions are a bit simplified. So I probably have to look more carefully about whether our assumptions imply strict feasibility. I don't think they do, but I will check.
Yeah, or let me say it the other way. Perhaps if you assume strict feasibility, then you can get the kind of things that Hamza was talking about. Right. But maybe without assuming it, then I think it would be too much to expect that.
I see. Yeah, maybe. But as I mentioned before, the techniques are not going to allow us to get this polylog epsilon accuracy.
So there's no refined version of those results, because in those tube results, right? The variety could be extremely singular, right? And those results, if variety is nicer, then are there like?
I don't think so. Mm-hmm. No, I don't think that there are not too many results in this area.
I see. Great.
Can you also, is there any thing that you can say about when you can get second order guarantees? What does it mean?
Oh yeah, so what does this mean? So this means that somehow the Burer-Monteiro method is not a single method, because in principle we can use any local optimization method to solve the non-convex problem. But our polynomial time guarantees are not going to apply to any local optimization method. We know that we need a local optimization method that satisfies some properties, some second order guarantees. And in our paper, we gave an example of one method that satisfies the second order guarantees. We believe that there are probably more, but at the moment I don't think that there are many results regarding methods with second order guarantees for QCQPs.
So if you have a second order guarantee, that means you have essentially optimality with respect to perturbations, I think.
By second order guarantee, I mean that that the second order the KKT conditions are satisfied with second order, that the Hessian of the Lagrange will be positive semi-definite on the tangent space.